we have studied the half part of module number 3, angular momentum. Today we will see the remaining half part of this module. We will start with matrix representation of angular momentum J in basis which formed by Kate state of Jm. Kate Jm is the state of system, and when the number of states are combined, it forms a basis. For the matrix representation of capital J, eigenkets and operators will represented by column vectors and square matrices respectively. To find matrix representation of J, we consider J square and Jz. For that, set of common eigenstates can be chosen as a basis formed by Kate Jm. As the operators J square and Jz are the diagonal in given basis, they are given by their joint eigenstates as follows. Here, joint eigenstates are J dash m dash and Jm. Firstly, the operator J square is operated on state Jm, and then the brass state J dash m dash is jointly operated with state Jm, and we get h cross square J in bracket J plus 1 into delta of J prime J into delta of m prime m. Similarly, when operator Jz is operated on state Jm and brass state J dash m dash is operated on it, then we get m h cross into delta of J prime J into delta of m prime m. M h cross and h cross square J in bracket J plus 1 are the diagonal elements for Jz and J square respectively. For small j is equal to 1, the m takes value minus 1, 0 and 1, and we get matrices for J square and Jz. Here, k top 1 minus 1, k top 1 0, k top 1 1 are the eigenstates for J square and Jz. Last point of this module is Clebsch-Jordan coefficient. It commonly arises in the application involving the addition of angular momentum. The numbers which arise due to coupling of angular momentum are called as Clebsch-Jordan coefficient. Now we see how the Clebsch-Jordan coefficient, that is CGC, are represented in Dirac notation. Consider a state phi of Jm such that phi of Jm is equal to summation bra m1 m2 over Kate Jm state into psi m1 m2. Here, this summation term is called as Clebsch-Jordan coefficient. It is useful to find magnetic properties. Specifically, m1 and m2 represent the significance of magnetic properties. As the Clebsch-Jordan coefficient are results from the addition of angular momentum, the total angular momentum is given by capital J is equal to addition of orbital angular momentum capital L and spin angular momentum capital S. For two electron system, the angular momentum are J1 and J2 respectively. These are some formulae to find Clebsch-Jordan coefficient for two electron system, where J plus and J minus are the raising and lowering operator of angular momentum. Let us find Clebsch-Jordan coefficient, that is CGC, for small j1 is equal to plus half and small j2 is equal to minus 1 half. For two values plus half and minus half of j1 j2, j takes values 1 and 0. Firstly, we have to find phi of jm state. For j is equal to 1 and j is equal to 0, the states are phi of 1 1, phi of 1 0, phi of 1 minus 1 and phi of 0 0. Given selection rules are considered while finding Clebsch-Jordan coefficient. We also find the values of psi m1 m2 as psi of 1 half 1 half, psi of 1 half minus 1 half, psi of minus 1 half 1 half and psi of minus 1 half minus 1 half. Clebsch-Jordan coefficient for minimum and maximum values of m1 and m2 are always equal to 1. Applying this formulae, we can find the Clebsch-Jordan coefficient for different states, and the resultant outcome of Clebsch-Jordan coefficient is shown in the table. From the table we can observe that the value of Clebsch-Jordan coefficient for maximum and minimum state is 1.